Welcome to the video lecture series Digital Electronics and Circuit, paper code S3DE for Diploma Second Year, BCAN 101 for BCA First Year. Myself, Mrs. Mopali Roy, Assistant Professor, EC Department, Narula Institute of Technology. This is my lecture 32. From the previous lecture or up to the previous lecture, we are starting with the sequential circuits, and now we are applying the sequential circuit. That means we are applying the flip-flops as the counter register. We know about the shift register and we know the application of the shift register from the previous lecture. That is the basic application of the shift register, serial in, serial out, or the serial in, parallel out. In that way, that is the ring counter, Johnson counter. So the up to this we know about the shift register. Now we are come to the sequential circuit or the sequential synchronous counter. That means now we are come to the non-shifted register. That means the synchronous counter have two parts. One is the shift register, another is non-shifted register. Now we start with the non-shifted register. Basically, all counter have some logic to design. In this one also we are discussing about this, that how, that means in this lecture we are basically know that how the counter is designed. From the previous one also we know that this is the circuit, this is the output, this is the waveform. But how we are getting the circuit? We are getting the circuit depending on the output or depending on the waveform. That means our output is our input actually to make the circuit. That means we know the input, we know the output, we have to make the circuit. So how we are making, actually what is the way to make the circuit, we have to know that. And first thing we have to know that how we can get the output. So from today's lecture we comes to know that how to design a counter. That means we have the output, we know the input, we have to make the circuit. So let's start. Mod and counter. Okay, so one by one what we can say, the job of the counter is to count by achieving the counters of the, that means the content of the counter by one count with each clock pulse. That means for depending on each clock pulse we have to count this one. So the counters which advance their sequence of the numbers or states when activated by the clock pulse, inputs are said to operate in a count up mode. That means we have to count in a proper way. So likewise, counters which decreases their sequence of numbers or state when activated by a clock input are said to operate in a count down mode. That means it have count up mode, count down mode, but the process is the same. That means we can count. Count means we want to count a number. Suppose we want to count 0 to 9 or 9 to 0. So if we want to count 0 to 9, that means we have to count up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we want to count down, then what we are doing? Count down means 9, 8, 7, 6, 5, 4, 3, 2, 1. So that is the countdown. So process is same, counting, but one is count up, one is count down, decreasing or increasing way. So that is also a work of a counter. So the counters that operates in both the up and down modes and called the bi-directional count. That means if a counter have both the process, that means using a single counter we can count up and count down. So this is called bidirectional. Otherwise, if a counter can count up, then it is called count up counter. If it can count down, then it called down counter. So, but if a counter can count up and down both, then it is called bidirectional counter. So the number, the state of the counting sequences through which a particular counter advances before returning once again back to the original or the first state, that is called modulus or mod. That means the basic concept of this mod. This n means how many number we want to count. That is the n. And these mod means the modulus, that means up to which state. So this modulus 9. So we want to count modulus 9. That means up to 9 we want, ninth number we want to count. 0, 1, 2, 3, 4, 5, 6. In that way, the ninth count, how many count we want to count, that is the nth point. And modulus means the state, up to which state. So this state is denoted as n. So mod n or modulus n. Modulus is shortly named as the mod 1. So what we are using, the modulus counter or simply mod counters are defined based on the number of the states that the counter will sequence through before returning back to its original value. For example, we can say a 2-bit counter counts from 00 to 11. That means if 2-bit, then 0001 1011. That means these 4 numbers they can count. So in case of binary, that means 0 to in case of binary, this is 0001 1011. That means in case of binary, it is 0 to 3. So it have 4 module, 0, 1, 2, 3. So it have 4 module there. That means 00, 01, 10, 11, and then return back to 00. So that means it have 4 module. So would they have called modulus 4 or modulo 4. So it is counting 4 numbers 0 to 3. So this is called modulus 4 or mod 4 counter. So note that is also take 4 clock pulse also. That means how many clock pulse it takes, that is also named as the modulo this number. Because if we are getting 00, that means using the first clock pulse we are getting 00. For the second clock pulse we are getting 01. For the third clock pulse we are getting 10. For the fourth clock pulse we are getting 11. So that means using 4 clock pulse we are getting this output. So how many number we are counting, that is also the modulo number, as well as how many clock we are needing, that is also the modulo number. So as this is a simple example, there are only 2 bits, that means n is 2. Then the maximum number of the possible output or the maximum number of the modulus is counted, that is 2 to the power n. So how many numbers are inputs of there? If there is 2 inputs, that means 2 to the power n, that means it is 4 also. So however, the counters can be designed to count to any number of 2 to the power n state in their sequence by cascading together multiply counting state to the procedure of a single modulus or the mod n counter. So whatever I said previously also, that how many number we are getting, that is the modulo n number. So therefore a mod n counter will require n number of flip-flops connected together to count a single data input, where providing 2 to the power n different output state. So n number of bits are there. Note that n is always in the integer value. So then we have to see that mod n count, that means mod counters have a modulus value, that is a integral power of 2 to the power n. That means 2 to the power n. So we are getting 2, 4, 8, 16, so on. We are getting the number. So n bit counter depends on the number of flip-flops used. So how they are connected determining the types of the connection or types of the counter we are getting there. Okay, so let's start. That is, suppose we are getting D types flip-flop, because we know using various types of flip-flop we can make the counters, but D or data flip-flop is more useful because whatever the input we are getting, giving, we are getting the same output. So we know data is given there, using the clock we are getting the output. That means clock, if clock is high, then if D is high, Q is also high. If clock is 1, D is low, the output is low. If clock is low, then there will be no change condition. That means totally depending on the clock, if we are giving any input, we are getting the same output from the D flip-flop. So that means if there is a logic 1, whatever I say, that logic 1, that means high on the data input, when a possible clock pulse is applied, then the flip-flop sets and stored a logic 1 at Q, and the complementary 0 we are getting, that is the Q1. So likewise, if there have a low on the data input, whenever the positive clock pulse is applied, then the flip-flop is reset. That means 0 becomes, that means it now 0 and Q bar becomes 1. So that is the basic concept of D flip-flop. So defining two counter and the timing diagram, what we can say, that is the D flip-flop. So if this is the D flip-flop and if we give the feedback there, that means D type flip-flop, we are giving the Q bar there. Then what we are getting for first clock pulse, when the initially, if what we are giving, if this one is 0, then what is there? This one is 1. So this one is 0. 1 now. So the output is 1. If the output is 1, then this is 0. If this is 0, then for the next clock pulse, what we are getting? We are getting 1 there. So now what happened? This one is 0. If this one is 0, then this one is 1. So now if this one is 1, for the next clock pulse, whatever happening, there is 1. So in that way, this is repeating. So if we are connecting Q bar as the feedback loop in case of D flip-flop, then we are getting the output for every clock pulse, that is 1 0 1 0 1 0. And the output, whatever we are getting, that is in a clock, half clock pulse, we are getting the output of this one. Okay. So that is the concept of this one. So the timing diagram shows that is the Q output waveform has a frequency constant exactly 1.5 of the clock input. Okay, so what is happening, that added another D flip-flop, what we can get, the output of the Q flip-flop, we are getting the second D flip-flop's output. So the output signal for the second D flip-flop would be the 1 counter of the clock pulse inputted frequency, and so on, because we are getting the half clock pulse. So using these half clock pulse, we are getting the more one. So for n number of flip-flops, the output of the frequency is divided. That means for in case of frequency also, we can get some what we can store something, or we can save some frequency, or save some inputs. So it's a, in case of nth number, we are getting 2n. So that is the advantages of D flip-flop. So now first we are modifying, that is mod 4 counter and its timing diagram. So see, this is the mod 4 counter, and what we are getting, we are giving the clock pulse. So D is there, and whatever the output, this is the output, and QD comes there. In the same way, QD bar is come there, and that is the output. That is that is LSB, that is MSB. This is the clock pulse, and this clock pulse is depending on this one. That means whatever the input of this one, this is the clock pulse. So if this is half, then this is the quartered one, what we are discussing before. So what we are getting, if that is 1 0 1 0 1 0 1 0, then what is the value of QB? For the first one, that is 0. For the second one, whenever it comes, then it is 0. So it is continuing. Then whenever it becomes 1, in that time, this is also, when it was on, then when this clock is on, then this is become 1. If this is become 1, then this clock pulses comes there, then this output comes there. So for 1 bit shifted, see, 1 bit shifted, that means if it is work in half, then this is the 1/4 counter. So in that way, this is QA and QB, and we are getting what we are getting. See, this is 1 0, this is 0 1, this is 1 1, then 0 0, then 1 0, then 0 1, then 1 1, then 0 1. So we whatever we are getting 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. So in that way we are getting, this is our MSB, this is our LSB. So in that way, mod 4 we are getting 4 output, 0 0 0 1 1 0 1 1, 4 output. That means mod 4 counter we are getting from this one. So from this one we are getting this. So how this, the switching transition of a QA, that means this one QA and this is QB, QA and QB, and the clock is the above timing diagram are shown, that means this one shown that simultaneously even they are connected and respected the asynchronous counter. This is, see, we are not giving the same clock pulse, so this is the asynchronous one. Okay, so for this, in relatively there would be it vary from the switching or delay between the application of the position or positive clock pulse is going on. So and the Q output, that means output is QA and QB. So QA and QB the outputs, and what is the output? That is LSB, that is MSB. Okay, so in that way we are getting mod 4 counter. So next one is state diagram. So this is the state diagram. What is state diagram? That is the state diagram depending on the present state, next state, whatever we are getting. So 0, start with this one. Initially the first one is 0 0. For the next one, that means the output of the 0 state, what we are getting? 0 1. That means the next state is this one. If present state is 0 0, then what is the next state? That is 0 1. See, if 0 0, if clock pulse is 1, then 0 1. If clock pulse is 1, then 1 0. If clock pulse is 1, then 1 1. If clock pulse is 1, then 0 0. So this is 0 0. Next clock pulse is 0 1. So now if the clock is 1 now, then what happened? Then the present state now 0 1. What is the next state? 1 0. For the next one, now this next state is the present state. So for this one, next state is the present state 1 0. For this one, what is the next state? 1 1. For the next one, this 1 1 is now the present state. So if this one is the present state, then what is the next state? 0 0. Now it is repeating. See, this is repeating there. Now this 0 0 is our present state. That means if we start with the 0 state, in case of 4th state, it is repeating. So this is the state diagram with the present state, next state table. So from this one, what we can say, the truth table of the counter and the regarding of this value of QA and QB, when QA is 0 and QB is 0, that means this is start from 0 0 counting. For the next one, after the application of the clock pulse, that means the first application of the clock pulse, the value QA becomes 1. See, this 0 is becomes 1 now, and QB remain unchanged. For the next counting, that given the counter 0 1, and after next state, the next clock pulse value is QA becomes 0. That means for this state, what happened? This QA for next state, QA becomes 0 and QB becomes 1. For this count, so for this, finally the value becomes QA and QB. That means this 1 1 1 counter giving the count 1 1 3, instead of 3 we are getting 1 1. So the application of the next clock pulse, what happened is repeating, that means 0 0. So what we are saying, that the application of the next clock pulse causes the counter return back to the 0 0 condition, and thereafter its count continuously up in the binary sequence. This is the up counting: 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. That means the sequence is up state. Okay, so in that way it is counting. So this is the mod 4 counter state diagram. Next, one is mod 8 counter and its state diagram. So see, this is the mod 8 counter and this is the state diagram. What we are getting, see, mod 8, that means we are getting 8 output there. So 0 0 0, then 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 1, 1 1 0, 1 1 1, repeat. So this is the state diagram of the mod 8 binary counter. And this mod 8 counter, how many numbers of flip-flops we are needing? We need 1 2 3 4, that means 2 to the power 3 number of counter we need there. A clock pulse we need there. This is the clock pulse from where we are getting the input. Then what we are giving? We are giving the feedback there, and this is the, so this is also a asynchronous mod counter. Okay, this is also a asynchronous mod counter. See, this is the output of this one, this is the output of this one. In that way we have flip-flop 1, flip-flop 2, flip-flop 3. So a natural count of the 2 to the power n state, giving the counter with the mod counter, that is 2 to 2 4 8 16, and then repeating. So it is necessary to have the modulus counter that reset it count back to 0 during the normal counting process and do not have the modulus in the power of 2. Okay, so that is the basic concept. Next, for the example, if we want to count 3 5 6 or 10, then what is the process? Up to this is okay. Then we want to count 4, we want to count 8, we want to count 16. If we want to count 16, then 2 to the power 4. That means we need 4 flip-flops. Up to this, that means we want 1 1 1 1. Then this is repeat to 0 0 0. But if we want to count 3 5 6 or these number, that is, it's not the representation of the 2 to the power n form, then what to do? Okay, then count of modulo small m. What is that? Okay, the counters either synchronous or asynchronous process, one count at a time in a set of binary processing, and as a result n-bit counters function naturally as a modulo 2 to the power n count. But we can construct mod counter to count any value we want to use one or more external logic gates, causing it to skip a few output states and terminate at any counts, resetting the counter back to 0. That means that all flip-flops have q equals to 0. If we want to count not in 2 to the power n form, then what to do? In case of that, the modulo m counter, they do not count all their possible states, but instead counting of this m value we return to 0. That means if we want to count 5 number, that means we want to count 0 1 2 3 4 up to 4 we want to count. That means we have to start with 0 0 0 0 0 1 0 1 0 0 1 1 1 1 0 0 up to this. Then after 1 0 0 we want to return back to 0 0 0. We won't want to count 1 0 1 1 1 0 and 1 1 1. We want to skip this one. So that is for this. What is the example? So obviously m number is a smaller than 2 to the power n. That means if 2 to the power, suppose we want to count up to 4, then if we take 2 to the power 2, then we cannot count this one, because 2 to the power 2 means what? We can 2 to the power 2 means 4. That means we can count 0 1 2 3 4 count, but here we want to count up to 4. That means 0 1 2 3 4. That means m value of m is 5 there. So 2 to the power n is equals to 2 to the power 3. That means 8. So now our n is 8 now. So n is less than 2 to the power n. That means for counting 5, we want to take 2 to the power 3 form. So how do we get the binary count to return the 0 part away through its counting? So fortunately, as well as the counting up or down counters can also having the additional inputs cleared, that is called clear and preset, which makes it possible to clean all the counters to 0. That means we can preset or clear as 0, or to preset the counter in our initial value as 1. So that is the application of mod M counter. So what happened? Mod 5 now. That means 2, 3, 3, 5. That means not like the N. Mod M. Okay, let's start. M, for this one, M is equals to 5. So 2 to the power, what I am saying before, that we are taking the 5 number or we are taking the 4 numbers. So mod 5. So 2 to the power N must be greater than 5. So 2 to the power 3, that is 8. These two are not greater than. So 2 to the power 3 is greater than 5. Then we need to count how many number of flip-flops are there. 2 to the power 3, that means we need 3 flip-flops are there. Flip-flops N is equals to 3 now. So using 3 number of flip-flops, what we can count? We can count 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So that means we can count 4 number 0, 0, 0 to 1, 1, 1. That means we can count from 0 to 7. But in case of modulo 5, what is our target? Our target is 0, 1, 2, 3, 4, up to 4. That means mod 8 counters truth table. This one, this is the counter, mod 8 counter. That means this one, 8 to the power 3, mod 8 counter is there. This is mod 8 counter, and that is the truth table for mod 5 counter. So that means we want to count up to this, not this one. So this 1, 1, 0 is stop there. So we want to count 0, 0, 0 to 1, 0, 1. So for this, what we have to do? We have to use this one, mod 8 counter. Then what is the changes of this circuit? So what is this? See, this is the circuit. And how we are getting this? See there, what we are getting? Initially, we are getting this one. That means, see, this one is 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Up to this, we are counting. Again, what happened? There, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Up to this, we are counting. So in that way, we are getting this one. And how we are getting this circuit? In the previous slide, see, this is the input. So what is the process to get this mod counter? We have to use the excitation table. That means the excitation table for any flip-flop. What flip-flop we are getting there? We are using D flip-flop. So what we have to use? We have to use the previous state, that means present state and next state. What is we are making there? That is the state diagram. We are using the state diagram now. So from this, we have to use the state diagram for this one. And so let's check about the state diagram. If we want to check, then what we are giving? We are getting 0, 0, 0. Then we are getting 0, 0, 1. Then what we get? 0, 1, 0. Then what we get? 0, 1, 1. Then what we get? 1, 0, 0. Then what we get? 1, 0, 1. Then what we get? We are getting this one. So if the present state is 0, 0, 0, then next state is 0, 0, 1. So this is QA, this is QA, QB, and QC. This is the LSB, this is MSB. So this is the main target. So up to which we want to count? We want to count 1 0 1. Then the next state is 0 0 0. So that is the truth table. So 1 1 0 up, and 1 1 1 is don't care there, and we are using D flip flop there. So whatever the input, that is our output there. So using this one, if this is the output, so for this one truth table, one equation we are getting. For this one equation we are getting. From this one we are one equation we are getting. Using what? Using K-map. So using K-map, we are getting 3 individual outputs for this one, and this one. So whatever the output we are getting, that means the input of this one, input of this one, and input of this one, whatever the output we are getting, that is the circuit of this one. So what we are getting? See, we are getting that this one, this Q is comes there. Then we are making this one, and from where we are connecting? We are connecting in the clear section. So in that way we are clearing this one. After which one? After this 1 0 1 condition. So used our 3 input AND gate, that is this one, using these 3 input AND gate to decode the 0 1 0 state. What? In case of 0 1 0 state, that means this state, what we are getting? We are decoding this one. But the first time QB and QC both are logic 1 in the 6th condition. So what happened? 2 input AND gates connected to QB and QC could be used without the complementation of the 3rd input and the inverter. So in that way, whatever the circuit we are getting, or whatever the output of we are getting clear, we are clearing the output after this 1 0 1 condition. Okay, then we are getting this one. In the same way, we are getting the decade or modulo 10 counter. How we are getting? A 4-bit decade binary counter. This decade binary counter is also when we are discussing the synchronous counter. In that time also we are using this modulo 10 counter. Today we are discussing the first part. A 4-bit decade counter. This is the circuit of 4-bit decade counter. We are logically giving the 0 there. And what is this one? The clock is, this is the, here we are using the asynchronous one. See, this is the asynchronous input. This is the asynchronous clock pulse. When we are discussing about the synchronous counter, in that time we are making this way in the in case of synchronous one. So the output is from decade counter. That means modulo 10. Decade means we want to count 0 to 9. Only that 10 output we want to get. So this is the way. For the first one, whatever the output, second one, whatever the output, the third one, whatever the output, there is no problem. Only the changes is there. So what we are getting? We are using a NAND gate there, and using this one, we are clearing the output. After which one? That means our target is 0 0 0 0 decade. That means we have 4 input 10. That means 2 to the power 4. We want to need 4 flip flops. We are using F1, F2, F3 and F4 there. So we start from 0 0 0 and count up to 1 0 0 1. So in case of 1 0 1 0, we have to clear this one. We have to clear this one in that state. So what we can say, the additional AND or OR gate detects that when the counting sequence reach to this one 0 1 0 1. That means the binary 10 and its clause the flip flop 4 toggled in the next clock pulse. This flip flop 4 is toggled for the next clock pulse, and this is the clear one. So the flip flops 1, that means this one is toggled in every clock pulse. Thus the counter is reset now and start to over again in the 0 0 0 0. Okay, so that means after in case of a asynchronous decade counter. Okay, so in case of asynchronous decade counter, that is the circuit for this one. Okay, So up to this is the lecture. These are the references from where you can get, or you can get the knowledge about this one, more knowledge about this one. Up to this is the lecture 32. If you have any types of query, feel free to contact me. This is my mail ID and WhatsApp number. Up to this, we are discussing about the how to design the mod counter, mod n counter, mod m counter, all this, and what is the process of this one. Okay, thank you.